So we left off on Wednesday talking about nonparametric bootstrap, and we are looking at this data set for immigrants from Latin America, and we are looking at their educational achievement level and whether they are from Mexico or not. Okay? And so when we did this, we found that on average, those who did not come from Mexico have a slightly higher educational achievement level than those who did come from Mexico. And, we are always asking, is this observed difference from our sample of 5.92, is that something that could have been a result of random chance while the two groups have the same mean, or is it something that's different? Okay. And so we ran nonparametric bootstrap, and we said in nonparametric bootstrap we are going to throw everybody in the same population. Okay. Nonparametric bootstrap is operating under the assumption that everybody comes from the same population, and we are going to just randomly sample from this population. And we randomly sample with replacement, and that effectively takes the sample that we have and makes a million duplicates of it, creating a large population from which we can draw a random sample. Okay, and so to do that, we said our pretend population will be the achievement levels. We're going to create a vector of 10,000 values to store, and within each vector, what we're going to do is we're going to take a random sample from this population with replacement. We're going to split those into two groups, and we're going to take the difference between those two means. Okay, and we did this 10,000 times, and we said, how often was the absolute value of our difference greater than our observed difference? And that happened about 4.7% of the time. If we were interested in a one-sided test, here a one-sided test would imply that we are expecting those not from Mexico to have a higher educational achievement than those coming from Mexico. Then we have an approximate p-value of around 2.7%. Okay, so this is what we have so far. This was kind of done using this manual process. Okay, and I'm hoping the code and the manual process is simple enough for us to see what's going on of how the nonparametric bootstrap works. Right, we're literally sampling, pulling a random sample from our population and working that way. Okay, this R has a library called boot, which does bootstrap. Okay, and the code to do bootstrap using library boot just runs a tiny bit differently, but this is a function that somebody else has built, or a package that someone else has built, but it works well. Okay, and so to load that up, you would run library boot. Okay, and if you look at the help for boot, so inside boot there is you'll see that the arguments for boot are that it requires data. That makes sense. Okay, and then the second thing is called statistic, which is a function. Okay, and then R is the number of replicates. Okay, and so the way the function works is it's going to return the statistic that you want. Okay, and the statistic is going to take at least two arguments, being the data and the indices. Okay, and so the way so over here, when we did the manual bootstrap, I did a random sample of these values from pretend population here. Okay, what the boot function does is it takes a look at the data, and it says, oh, there's 150 rows in the data, right? Because our data is going to be our data frame Latino. Okay, so if I look at dimensions of Latino, it sees 150 rows. And so what the boot function does, it says, oh, there's 150 rows. I'm going to sample from 1 to 150 times with replacement. Okay, and this is basically the indices that it's going to use. So this is what boot does. It takes it says, oh, there's 150 rows. I'm going to randomly sample from these rows. Okay, and it uses this as the indices, and it subsets the data using these indices. Okay, so when it subsets the data using these indices, that effectively is the same as running a sample right here, right? It's like sampling, taking a sample on the data. So from there we say our new data that we're looking at, we're just going to call it D. That's just a placeholder. You can call it whatever you want to call it. We're going to say this is our data, and then to get the difference between our two mean groups, we're going to say the first 34 belong to group 1, and then the remaining 116 belong to group 2, and we're going to take the mean between those two differences. Okay, so we're going to say D $ achievement 1 through 34, D $ achievement 35 through 150. Calculate the mean of those things, give me the difference, and that is the statistic that we're returning. Okay, so if you want to use the boot function, you just have to create a new function based on the data and the indices. The boot function is always going to generate a bunch of indices as part of the Bootstrap process here, and then we subset on that. Okay, so let me just run this. Okay, so this is the function, and we're going to just run nonparametric bootstrap. We run boot. Our data is the Latino data frame. Our statistic is this function that we created. We're going to create 5,000 replicates. Our book talks about, in Bootstrap, there's a little bit, they have a correction factor, which is why the boot, they're only running 4,999 rather than 10,000 replicates. It doesn't really matter. When you have 5,000 replicates, the correction factor makes hardly a difference. So, okay, so it runs right there, and then we can plot the density of our results. Okay, let me just talk about the results of the boot function. Okay, so when the boot function returns a list. Okay, so let me just do structure of nonparametric boot. Okay, it returns a list of class boot, and we can see kind of the pieces of here. Okay, it has all sorts of things. One of them is going to be T. T is basically our equivalent of this difference vector that we created. So over here we created a vector of differences that kept track of all the differences that we observed every time we ran a Bootstrap replicate. Okay. In boot, what it returns, whatever it returns in $T is basically that equivalent. Okay. And then it keeps track of other things, including the entire data set that it used, all of the seeds, a bunch of seeds that it used, and just a bunch of different things. Okay. So we don't have to worry too much about it, but we're going to just take a look at nonpar boot $T, and we're going to ask, what's the mean difference that it observed here? Got 0.01888. The standard deviation of this thing is that, and kind of an estimate of our p-value here of around 0.047. This is just how many of our differences are greater than our observed difference. Okay, and if we didn't want the absolute value, we could get rid of that, and we can see these are all quite similar. Compare this to what we had when we did it the manual way, and we did it 10,000 times the manual way. We're seeing, the values that we get here when we ran it manually are, very similar to the values that we got when we're using the Bootstrap package. Okay, so the Bootstrap package is also effective. Just different the code that you have to write is a little bit different, right? Okay. Okay. We're getting, as part of homework 6, I'm going to give you a decent amount of reading to do from our Comparing Groups book. And these examples in class follow the book examples along quite closely. And one of the things it talks about is looking up effect size. Okay, so are you guys familiar with effect size? Maybe you learned it in 101B, talking about the differences. Okay, so here we're looking at the education achievement level of Mexican immigrants and education achievement of non-Mexican immigrants. Okay, and we want and in our samples, random samples that we took, we observed a difference of 5.9, whatever that means. Okay, and we want to know, is this a significant difference or not? So one is this difference, could it have been a result of randomness? That's basically what we're asking when we do our randomization tests or our bootstrap tests. And then the other part that we want to ask is this difference even important? Okay, if a difference of 5.9 really doesn't mean anything, if it's like the difference between 1 extra month in school or something, maybe it doesn't really matter, or maybe it is a significant difference. Okay, and so one thing we can test is we can kind of test a series of hypotheses of different effect sizes. Okay, so the first ones that we've been testing have all been that the two groups have the same mean, that there's no difference between them. Okay, that we're testing it against kind of the null hypothesis that the effect size is 0. But we might have a thing where we say, well, what if it would be important if the effect size is, I don't know, it's really only important if the effect size is 4 or greater. Okay, and we want to know, okay, well, is 5.9 significantly different from an effect size of 4? Okay, and we can ask questions like that. Or maybe you're expecting an effect size of 12, okay, where you're expecting that these two groups have a difference of 12, and then we want to know, is 5.9 significantly different from 12? And we can kind of test these different things. Okay, and so here we can do this, and we can just say, like, well, okay, our first one, we want to see if the effect size, if the observed difference that we have, is that different from kind of this effect size of 3. Okay, and so if you look at the code, this is doing it the manual way, hoping to illustrate exactly what's going on. We're basically doing the same process. And what it looks like in effect, not this graph, when we do our density. So this is kind of the density of all those 10,000 observations. Right now, we're at 5.9, and we want to know, is this, oh wait, this is not it. Hang on. Plot. So I have density of our difference. Okay. So under the null hypothesis, we're expecting a difference of 0. Okay, and what we observed was a difference of 5.9. And right now, if we shade in the area to the right, we're going to get around 2.7% to the right of 5.9. Okay, and effectively, what we're going to do is we're going to just shift this distribution along the x-axis, and we're going to say, okay, is 5.9 still significant if the effect size is hypothesized to be 3? Is it significant if the effect size is 5, or hypothesized to be 5? Will it become significant if the effect size is hypothesized to be 12? Things like that. Okay, and we're all going to be looking at 5.9 or something more extreme. And so effectively, what we're going to do is we're going to just run this thing over and over, and we're going to just kind of shift it along. And right now, our p-value definition, or our p-value is something like our data or something more extreme. So at this point, it's going to be the area to the right. But as we shift this along, it's going to switch over to the area to the left. Okay? When, as this shifts along and 5.9 starts to move over here, we're going to want the area to the left as these numbers kind of shift along. So let me just kind of show you what we're going to do. We take our vector of achievement levels. We're going to create an empty vector of differences. Here I'm going to just start off with a parameter of 3. And, whoops, where did it go? Okay, I'm going to just take random samples of 150, split those into 2 groups, take the difference between those 2 groups, and I'm going to just add on the parameter. Okay, and this throws in this effect size here. And here we run that. Okay, and so here, plot difference. Did I do something wrong? Parameters 3. Okay, here we go. Okay, so I've done this. All right, and so now now it's centered at 3. Okay, and we want to know. Let me just do AB line V equals 5 point. Is it V? No, I don't know. I think line. How do I add a line? Okay, well anyway, I won't. Just to pretend there's a vertical line at 5.9, and we can see that the area to the right is now going to be much greater than before. Okay, and so we can just kind of say, like, how many times was our area greater than our observed difference of 5.9? 1,600 times, so that effectively makes our p-value of around 17%. Okay, and we can see our mean difference is now really close to 3, as we expect. Our standard deviation is not very different from before, also close to 3. And we can kind of change this along and say, like, as I move along, if I hypothesize a difference of 5, and I want to know, is 5.9 significantly different from 5? And we plot this. Okay, we look at 5 and compare that to 5.9, we'd see, okay, no, it's not significant. It's not significantly different from 5.9. And we get a p-value of 38%. Okay, so we see, okay, we're not going to have much evidence of a difference there. Okay, so we can also do the same thing using the boot function. So here's, I'm just tacking on 3 to see, what kind of values I get. Again, I've just subset my data using the indices, and I'm going to calculate the difference between the means there. We run the Bootstrap model. We ask what's the mean here, standard deviation, right around there. And here they got around 17% for a p-value. And so maybe we're curious, like, okay, what is a range of effect sizes where 5.9 is not significantly different? So this kind of creates like an interval or a confidence interval of effect sizes that are plausible with our observed difference of 5.9. Okay, so when we had a difference of 0 or an effect size of 0, 5.9 was significantly different if we used a one-tailed test. On the other hand, we might be asking, what other values are allowed? So I'm going to create a results matrix, and the results matrix will go from the values 0 through 12, so there's 13 rows, and for each value that I'm testing, I'm going to look at, we're going to find the p-value, the mean, and the standard deviation. So my results matrix looks currently like this. There's no values in here. We're going to test for effect sizes of 0 through 12 with all of these different things. Okay, and for each one, I'm going to just basically run the same code over and over again. I'm going to just take randomly sample, put them into 2 different groups, and the difference that we're going to get will be the difference between these things, and we're going to add on the parameter there. So effectively, I'm just taking the thing and I'm just shifting it along. And each of the parameters that I'm going to test will start off at j minus 1. So we're going from 1 through 13, so it's going to go from 0 to 12. Okay, and then when we calculate the end, the p-value is going to be whether, what percentage of the differences are greater than or equal to our observed difference, or less than or equal to our observed difference. And it's going to switch from greater than or less to less than when the effect size, crosses over our observed difference. So while it's smaller than our observed difference, we're going to look at the area to the right. And then when our parameter effect size is greater than the observed difference, then it's going to look at the area to the left. So we run this, and so this is going to run 10,000 replications 13 different times, so effectively 13,000 replications. It'll take, a moment here. This is with modern technology, it goes very quickly, okay? And now we look at our results table. Okay, and so if we hypothesize an effect size of 0, meaning that the difference in education achievement levels between those from Mexico and those from other Latin American countries is 0, then the p-value for getting our data, or something greater than that, is around 0.024. Okay? As we shift along, we can see that the area will get larger and larger, and so our p-value kind of shrinks. And it's quite large at an effect size of 6, which is expected because our observed difference is 5.9, and so 5.9 is probably not going to be very significantly different from 6. Okay? But as it shifts along in the other direction, it starts to get smaller and smaller, down to when we're at around 11, the difference, the p-value is small, and at 12, then it becomes significant again. Okay? And so we want, if you wanted to kind of create a 95%-ish confidence interval of effect sizes that are not significantly different, or where 5.9 is not significantly different from the effect size, we would say, effect sizes from 1 to 11 would be plausible. Okay, because here, right, a 95% confidence interval, you'd have 2.5% in this tail, 2.5% in the other tail. Here we're getting, p-values of over 2.5% at 1 through 11, and then it's only down at 0 and 12 do we get p-values that are smaller than that. Okay, and we can see that the standard deviation of all of these things remain quite constant around 3, and our mean moves right along from 0 to 1 to 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? And so so this is what we get. Okay, we could do the same thing using the boot library in R. Creating the same results. We'll call this results 2, or I don't know. Yeah, just so we can compare results and results 2. So this is our matrix. We're going to create an empty one, same values, and we're going to just run the same thing. This time, every time I run one of those iterations, I define a new function inside each loop, and it uses the same thing as before. It's looking at the data. We subset our data based on our indices, and then we throw that into just calculating the mean here and tack on the parameter. We run this, we run the boot function on this, calculating our statistic, and then we get all of these things. Okay. The boot libraries function keeps track of a little bit more than kind of our manual method, so it is actually a little bit slower than kind of our manual thing. But it runs, and we'll take a look at our results, and they will be quite similar. Alright, so we'll take a look at results 2. Okay, so let me so looking at results 2 versus our first results table, we can see that the p-values are all, very similar to each other, okay? Around 2%, 5%, 9%, 16 versus 17, 25, 25, 37 over here, 38, 48, 51, okay. That could happen. 35, 35, 23, 14. They're all quite similar, using whether we use the boot library or kind of our own manual function, because effectively what we're doing is the same thing. It's just R has its own library that does this. One advantage of the boot library, though, is that we can use some confidence interval commands that the boot library implements, and so we'll talk about that. Okay, so again, over here with multiple effect sizes with the boot package, we're all kind of testing the null hypothesis that the difference between the two means is some effect value. Okay, if it's not 0, it's some number 5 or 4, whatever it might be. Okay. Another approach to this is not to treat it as if we have a null hypothesis where the effect size is some value, but and they're coming from the same population, but rather that that our samples have come from two separate populations. Okay, and so in this case, we're going to treat those coming from Mexico as population 1, and we're going to say that has some mean value mu1. And those not coming from Mexico but other Latin American countries will be population 2, and those values have some mean value mu2. And then we can make a confidence interval for mu1 minus mu2, a difference between the two means. And so the way this is going to work, if we did it the manual way, is we would subset our vector of achievement scores where the people came from Mexico. Okay, and I will store that in this vector Mexican, and then those who did not come from Mexico, we will take those achievement scores and we will store that in a vector called non-Mexican. Okay, and so I can take a look at these things, and we'll see that there's 116 values in Mexican, and so on and so forth, and all of this stuff is as we expected before. And we're going to create two random samples. Okay, we're going to randomly sample from this vector of 116 values with replacement, effectively treating this as its own population, and we're going to take that random sample and store it in random sample M, and then we're going to take the one for the non-Mexicans. We have 34 over here, and we can treat this as its own population, randomly sampling with replacement and storing that vector in random sample NM. Okay, so here, so before we threw them all into the same population, right? We said pretend population was all 150 scores bunched together, and then we sampled from that, and then after we took that big sample, we split it into two groups. Here we are going to keep these two groups separate, and we're going to generate a new sample of 116 from these and a new sample of 34 from these with replacement. Okay, so there is a subtle but an important difference there. Okay, and so we do that. We're going to I'm going to take a random sample there, take the difference between those two things, and I get a difference of negative 6.62. Okay, so that is different from our observed difference. Remember, our observed difference is 5.92. Okay, and if I ran another Bootstrap sample, did a random sample from group 1, random sample from group 2, calculated the difference of those two means, I would get something else. Over here I get negative 4.29. Okay, And so we can run this many times, 10,000 times we can do it, and we will get an idea of the amount of variation that we would see. So here I can do this 10,000 times. Each time I would take a random sample from the two groups, calculate the difference between those two groups, and store that in our vector of differences. So we do that, and I look at this, and it doesn't look very different from all of these other things, okay? And that's because of the central limit theorem saying everything's going to end up looking normal, at least when you're dealing with the mean, and that is quite what we observe here, okay? And so here we're getting a mean difference of 5.92, which is what we expected, okay? The standard deviation here is a little bit smaller. It's 2.6 versus 3, okay? Or something around 3, and that is because we are limiting the samples that we're taking. We didn't throw them all together, and we're taking the samples separately, and so that will reduce the amount of variance that we do see, okay? And so one way to kind of get a confidence interval is using quantiles. So we did this 10,000 times, and we can say, okay, we can look at the 2.5th percentile and the 97.5th percentile of our 10,000 replications. Okay, and that will kind of give us an idea of the middle 95% of differences that we might observe just from kind of resampling this over and over again. And so when I do that, as far as the quantile differences go, or the differences go, the 2.5th percentile is around 0.6, and the 97.5th percentile is right around 11. Okay, and so this is one way to kind of get a confidence interval based on our many replications. Okay, we could do this with the boot package. Over here, we subset our data using our indices, and instead of assigning just the first 34 and the last 116, we are going to subset them actually based on whether they are from Mexico or not. So here we're going to use subset using Mexico is equal to 0 versus Mexico not equal, or Mexico equal to 1. Okay, and then when you run the boot function, there's an important thing that we have to specify. Same thing, data and the statistic is this thing, but we have to say we're going to run strata. Okay, kind of like stratified sampling. We're going to say, when you take the random sample, rather than just randomly sampling 150 points, I want you to randomly sample those where for each strata in the Mexico vector, which would be zeros and ones. So for those from Mexico, strata those ones, and then those not from Mexico, do a random sample of those. Okay, so that will create 34 from non-Mexican countries and 116 from Mexican countries. So we run this, and it goes, and then we can take a look at our densities there, and so we can see they're quite similar between our manual method and using kind of I don't really know what the difference is. For some reason the axis shifts just ever so slightly, but the pictures are quite similar. We take a look at the mean and the standard deviation. We're getting similar values here. Okay, and I could do kind of the same thing. Instead of quantile on the differences, I can do alt model boot $t, and I get similar values here, 11 and 0.7. Okay, there are a series. So creating confidence intervals based on Bootstrap has been something that's been studied, fairly extensively, and there are different theories as to how to best calculate a confidence interval. So the method that I showed you is kind of like the quantile confidence interval, and some people say this is not the best way. I understand what they're saying, but really, when you're doing Bootstrap, you're generally not going for exact answers. You're depending on the randomizing process of the computer to kind of get you a ballpark answer of what this is, right? And anyway, confidence intervals, these are rarely like exact answers. But as far as Bootstrap confidence intervals, there's a variety. You can do normal, basic, studentized, percentage, BCA, and I can kind of show you some of these ones that we'll see. So if I do a Bootstrap confidence interval, you take the Bootstrap output from our previous part, and we say, you know, here is a BCA confidence interval, okay? And so we see it's, you know, subtly different from using the quantile method. There's normal, whoops. Okay, well, sometimes, oh, not normal, but norm. Okay, and again, this one also a little bit. This one's a little bit wider. Studentized requires something else. Okay, so this is the percentile ones using. This one's probably the closest to. I don't know. They're all just subtly different. These different types as far as Bootstrap confidence intervals, but they're also very similar. Okay, and so, you know, there's a little bit of theoretical discussion as far as how to best get a confidence interval from Bootstrap. Bottom line is they're all going to be quite similar to each other, and I don't. On a practical level, I don't know if it's if it really makes a difference. Okay, and I'm not a firm believer in, as far as statistics goes, I'm not a firm believer in having very strict, harsh lines, right? Like, I know in your intro stats class, this is kind of what we teach, and we say if it's bigger than 5%, then it's not significant, and if it's smaller than 5%, then it is significant. But, you know, then if you follow those rules closely, then 4.9% is significant and 5.1% isn't, okay? Or 4.99 is and 5.01 is not. And I don't think, I mean, that could have been measurement error causing that difference there. And I don't know if that's really the best way to go. So, you know, all of this discussion about the subtle differences between Bootstrap confidence intervals, I mean, I can appreciate that, but at the same time, if the value that you're looking at is like 10.8 and you want to know, well, is 10.8 significant, and under this confidence interval it's inside the thing, and in the other confidence interval it's not, you know, you should just be a little bit wary and say, like, well, if it's kind of at that borderline, what does that mean? I think as people, we like to have nice little neat categories, but things don't always work out as nicely and neatly as we might wish. So, anyway, this is doing some Bootstrap stuff. I'll post up all of this code on CCLE to make sure. I'll get homework 6 written up, and I'll kind of have you guys do a bit of reading in that one, and so we'll end there, and I'll see you guys on Wednesday.